EmDrive really started with a chap called Professor Eric Laithwaite, and in 1974 he gave a lecture at the Royal Institution, Christmas lecture, in which he claimed that a gyroscope could be used as a thruster. The Ministry of Defence suddenly got interested in this and wondered if it could be used for missile control, which was the sort of thing we were working on. So they came to us to evaluate the concept. Now we looked at it very carefully and decided that no, it couldn't be done mechanically. But I did then put forward a suggestion that it could be done electromagnetically. Once I'd convinced myself that the theory was correct, I carried out a little bit of experimentation in my garage in the traditional way. And then I explained the concept to my employers, who were at that stage Matra Marconi Space. Technical director rejected the idea outright and actually suggested that if I mentioned it again, it would my career would suffer. So at this point I decided to leave Marconi and set up my own company, Satellite Propulsion Research Limited. And along with a group of long-suffering shareholders, we started our work on developing EmDrive. Well, we were soon awarded a grant from the UK government, and they continued to fund this research. The work progressed through a feasibility study, which used an experimental thruster, through to a demonstrator engine that could actually produce 8 grams of thrust. In total, this was about a 5-year program, and we were pretty pleased with the results. So when New Scientist wanted to write a feature article, we agreed. The article was published in September 2006 and caused a bit of controversy. Well, I actually have no trouble with healthy skepticism. However, I was very shocked by the level of personal abuse that came back. And indeed, I still get some insults on some of these internet forums. But I guess I've got pretty immune to it now and just put it down to very strange people being out there on the internet. By 2008, we were involved in a number of meetings with the UK defence authorities. This culminated in a meeting on the 10th of December in the depths of the Pentagon. Fairly high-level presentation. It was attended by the US Air Force, DARPA, NASA, and it was actually chaired by the director of the National Security Space Office. The UK Ministry of Defence and the American Department of Defence are interested in EmDrive. It would clearly be very useful on any intelligence gathering platform or communications platform. Essentially, it provides good manoeuvrability, continuous manoeuvrability, with stealth characteristics. In particular, it enables low Earth orbits to be maintained, where which gives much better sensor resolution. And clearly EmDrive has no exhaust signature and therefore is inherently very stealthy. In the next decade, EmDrive technology will start to be being used all over the world. I think most people will only really notice EmDrive when they can call up a personal air vehicle. It will arrive and land vertically outside their house. It will take them wherever they want to go, quietly, comfortably, safely, and they won't get stuck in traffic jams. That's the sort of consumer application that we're looking towards. But there will be a much more serious application, and that will be when we can use EmDrive for low-cost access to space, and we can start launching solar power satellites. I mean, it's a no-brainer. Once you can get low-cost access to space, then you can solve the world's energy problems.
EmDrive Enabling a better future. This is just the intro. EmDrive, electromagnetic drive. What is it? Where did it come from? How does it work? What can it do? What happens next?
So, first of all, what is it? Well, essentially it is a propellantless thruster. Now, a conventional rocket achieves acceleration by expelling a mass in one direction, and the laws of momentum conservation means that the rocket will then accelerate in the other direction. What the EmDrive thruster does is to produce a force, which we call the thrust, in one direction. This is a force that you can measure. If you put your sort of hand against the end plate that's producing the thrust, you'll feel it pushing against you. And as with all machines that follow Newton's principles, it will therefore accelerate in the opposite direction. So this is not a reactionless thruster, because those things just don't exist outside of science fiction, but it is a propellantless thruster. In fact, it's the world's first propellant-free propulsion system. We originally developed it for spacecraft propulsion, and the public domain, if you like, now recognises that there are two major groups doing the development, one in the UK, which is ourselves, and one in China. Now, interestingly, these two groups have used different theoretical models. The UK group, my group, basically uses classic electromagnetic theory and physics. The Chinese group have tended to rely on modelling, three-dimensional digital modelling of the thrusters to derive the forces. But interestingly, the two theoretical approaches both give pretty well the same answer. So not only do the two different theories give the same answer, but two different sets of experiments also give the same answer. The UK group, ourselves, we've done we've built a number of thrusters, but the final flight thruster design gives pretty much the same specific thrust as the Chinese design. To most people, if you have two independent groups doing different work and coming up with the same answer, that is generally recognised as being a major step in the proof of any concept. Our work was originally funded in the UK by the government, and we then moved into a phase where we worked on private investment. And the end product of all this work was what we call a first-generation low-thrust technology designed specifically for in-orbit applications. Once the work has been pretty well agreed and established, we went through a process of transferring this work to the United States. This was done with UK government agreement. It was an export license approved by MOD. It was done under what's called a TAA, which is granted by the State Department, and in fact we actually transferred all our design and test data to Boeing. It's noticeable that any subsequent programs have not been acknowledged in the public domain. What we did in the UK was, having basically completed the research and development on the first generation, fairly simple low thrust technology, we moved into the really exciting area, which is what we call the second generation technology, where we're using superconducting cavities cooled by liquid gases. In fact, we built an experimental device cooled by liquid nitrogen, and showed that indeed this would give the theoretical levels that were necessary to give us the thrust levels that could be applied to launch vehicle and terrestrial applications. Okay, where does it come from? Well, in fact, the original concept goes back almost 40 years now to the depths of the Cold War, when we were trying to solve very difficult missile guidance problems, very important missile guidance problems for the strategic missiles, and we were actually encouraged to think the unthinkable. And it was during this sort of period, which is probably not encouraged too much these days, but we considered all sorts of approaches to the problem, and in doing so the concept of something like EmDrive came up. It was agreed that this had possibilities, but as always in these things, something else came along. It was actually satellite navigation, which solved the problem without having to resort to these rather wilder ideas. So it all got put away, and in fact it didn't come up again until essentially probably about 9-10 years later, when I was working on a military satellite called Skynet 4, and during the early design phase of this satellite, it occurred to me that a military satellite could make great use of something like EmDrive. Essentially, it gives you continuous manoeuvring capability using a propulsion system with no signature. Okay, so this was rather an exciting thought, and when I moved into project managing of these satellites, it also became very clear to me that it would save an awful lot of money and would ideally be useful on commercial satellites as well. At this point, the commercial implications of this sort of technology were not too impressive to the people I was working with, so we agreed to part company, and I left to develop EmDrive in my own company. And SPR Limited has been up running now for about 12 years, and in that period we've gone through a number of iterations. The main things that, the main milestones I suppose, have been an S-band demonstrator engine, a C-band flight thruster, and a second generation feasibility study. And if you're looking at the slides, you'll see what is the S-band demonstrator engine, the rather large looking device sitting on a turntable. It's one side is the thruster, the other side is an instrumentation platform, and the whole thing is sitting on a frictionless bearing and a very large air bearing. Now the total mass of that turntable is about 100 kilograms, and the objective of this was to demonstrate that we could indeed accelerate 100 kilogram mass in effectively weightless conditions using a reasonable input power. This is what we did, and the test video has been on the internet now for a number of years. The important thing is that this is a dynamic demonstration of EmDrive. It shows that indeed that it does obey Newton's laws, because it accelerates in the correct direction, and it also accelerates at a rate which is directly compatible with the static thrust that had been measured previously. So Newton can breathe again. Even we agree with him with our exotic EmDrive. How does it work? But essentially it is a resonant microwave cavity that has a truncated cone shape such that the guide velocity or group velocity, depending on how you wish to term it, is higher at one end than at the other end. This is all straightforward microwave physics, as indeed is the fact that because the group velocity is higher at one end than at the other end, means that you will get a higher force at one end than at the other end. Which is all sort of, as I say, straight out of a physics or microwave engineering textbook. There are, however, complications. The relationship between the wavelength of the propagated wave and the diameter of the cavity is very nonlinear, which means that any attempt to try and understand this with mechanical analogies like air pressure, it just fails. You do actually, unfortunately, have to understand the maths, and the maths is non-linear, and this does cause problems. But believe me, if you go through the maths, it works out correctly. What it does show is that you can design these things carefully such that you get a negligible axial component on the tapered walls. And you can also show that the net force on that you get out of this cavity, which gives you the acceleration, is dependent on what's called the Q of the cavity. The Q of the cavity is a measure of the quality factor of the cavity. Every system has a quality factor. You hope that a mechanical structure like a bridge has one that's much lower than 1, otherwise it would tear itself apart in wind. However, something like a microwave cavity can have a Q value of 50,000, which means that the stored energy inside this cavity is very large, and that the forces that are produced due to the so-called radiation pressure are also significant. They're not large because radiation pressure generally only produces very tiny force, but when you multiply them by the Q factor, then they become useful. One of the other things that that has to be taken into account is that obviously to be a practical machine, the EmDrive has to obey the conservation of energy. Now it does this because the forces are produced, if you like, by the stored energy inside the cavity. As you start to use up some of that stored energy in accelerating the cavity and thus producing kinetic energy, that stored energy will naturally go down. The definition of Q is stored energy over energy lost per cycle. Therefore the Q starts to go down, and therefore the thrust goes down. So it's a completely sensible system that does indeed agree with the conservation of energy. We've talked about the fact that thrust depends on the cavity Q factor. We've talked about microwave cavities typically having cavities Q values of 50 by 10 to the, or 5 by 10 to the 4, 50,000. But this is the classic microwave cavity made of copper or silver-plated aluminium at room temperature. Now, in any cavity, the Q depends on the resistivity of the walls. And if you can reduce that resistivity, then you will increase the Q. In a superconducting material, the resistivity is reduced close to 0. It's not actually 0, but it is approaching 0. And this means that a superconducting cavity can typically you obtain a Q of 1 by 10 to the 9th. Okay, so that's 5 orders of magnitude almost up on what we're getting with our room temperature cavities. This is quite well understood engineering. The typical high energy accelerator will use many hundreds of cavities, all with these sort of values of Q, so that superconducting microwave cavities can be considered even now as a manufactured item, indeed a sort of a reasonable high quantity manufactured item. So there's nothing too difficult about those. The problem, of course, is that any superconducting cavity requires cooling. What we propose is that for most transport applications, and indeed for most space applications, we would probably use liquid hydrogen as opposed to the liquid helium which is used in the high energy physics cavities. There's a big advantage in this because using liquid hydrogen to cool cavity means that as you boil off the liquid hydrogen, you can make use of the hydrogen gas in a fuel cell along with a bit of oxygen to produce your electrical power. And in the early designs of spaceplanes, and the one that you'll see, you can see that the hydrogen is also used for auxiliary propulsion. Now this 2G cavity with a vastly increased value of Q gives a step change in the thrust, and the sort of target that we look for is goes up from instead of, if you like, a few grams per kilowatt to a ton per kilowatt. So this then means that you have a propulsion system with a significant thrust to power ratio, one that can be used for all sorts of applications, and I guess the main space application that we're considering is a launcher, a hybrid spaceplane launcher. In fact, the design study that we did showed that we can come up with a 300-ton reusable vertical takeoff and landing launch vehicle capable of putting 50 tons into geostationary orbit regularly on a almost aircraft-like sort of cycle. Now, once you can start launching things into geostationary or into any orbit using what's basically commercial aircraft type approaches, the cost begins to tumble. You have large numbers of missions instead of the one. You don't throw away the vehicle as you do at the moment, and you have a ground infrastructure which is modelled on an airline rather than on a scientific launch. The impact of this will be that the cost of launching to GEO will be reduced from the current costs by approximately a factor of 130. And this, of course, is the thing that makes a significant difference to such large-scale applications as solar power satellites or any sort of geoengineering programs that use in-orbit technology. Okay, so what have we done to prove 2G? Well, we've built an experimental thruster. We've done a lot of design studies on various space planes and other vehicles, and showed that essentially it's all a reasonable extension of existing technology. Okay, so what can it do? Well, first of all, let's look at a first generation. This is a room temperature, uncooled cavity designed specifically for satellites. The short answer is that it should save of the order of £15 billion if you look at the satellite launches planned for the next 10 years, on the assumption that instead of using the traditional launch concept, we use EmDrive to take us from LEO, that's low Earth orbit, up to GEO. If you look at a classic 3-ton communication satellite, what surprises a lot of people is that over half the mass of that satellite is actually propellant. And this propellant is used to take the satellite from its transfer orbit, which is where the rocket puts it, into its operational orbit, which is where it starts making money. So if you can replace the mass of the propellant, or even get rid of the mass of the propellant, you clearly are going to reduce the launch mass and therefore reduce the cost of launch. The reality means that the mass of an EmDrive propulsion system, that's both primary and the so-called AOCS, that's the attitude and orbit control system. If you take the mass, the dry mass of an EmDrive propulsion system, it just about equals the dry mass of the existing propulsion system. So what you're actually doing is you are simply getting rid of the mass of the propellant. In terms of real measurements, you're getting rid of about 1.7 tons of mass from a classic 3-ton satellite. So you reduce the launch mass to 1.3 tons, therefore you use a smaller launch vehicle, or alternatively you can put more satellites on the same launch vehicle. You essentially launch it to low Earth orbit instead of its transfer orbit. You deploy the solar arrays and antennas in low Earth orbit, which means that you do have at least some chance of recovering them if this goes wrong. Deployment of these arrays and antennas is always the critical thing in the launch sequence of a typical communication satellite. So you've got your arrays deployed, you've got power feeding now into the EmDrive propulsion system, and you can use the thrust to spiral out from LEO to GEO using a so-called Edelman transfer in typically 36 days. Once you're in orbit on station, you can use the technology for station keeping and attitude control, and this means that you no longer are restricted by the reserve propellants for operational life. It does give you the opportunity of having much longer operational life for your satellite. So that's first generation, pretty straightforward. Technology is, if you like, now established. It's just a matter of waiting for industry and the user community to catch up. What is much more exciting and interesting is what a second generation EmDrive can do. And we've actually touched on this before, but the primary application that we see is to make use of it as a propulsion system in a unmanned carrier spaceplane. In essence, we would use a very high thrust EmDrive engine to provide lift to this vehicle, and once it's actually reached geostationary altitude, you would then use conventional rocket to put the orbital module into orbit with the necessary orbital velocity. You don't actually accelerate the whole vehicle to orbital velocity. You merely use it as if you like, as an elevator to get you up to the launch, up to the operational altitude. So what we're saying is that we will use the EmDrive as a lift engine. This will lift the carrier vehicle to the altitude. It will do it gently and efficiently, rather than in the rather brutal manner that is a classic launch vehicle. And once it's at the altitude, then you'll use a conventional rocket to accelerate you up to orbital velocity. Now, because you're obviously accelerating in vacuum by then, you're at 36,000 kilometres. Clearly, it's a very efficient way of getting orbital velocity. Essentially, this gives you a very large reduction in launch cost. It makes for a very simple, low-stress launch vehicle, and the big application that we see is solar power satellites, because suddenly solar power satellites become not only economically viable, they become something like about a tenth of the cost of a nuclear power station for the same electrical output. We've mentioned before that the actual EmDrive cavities are cooled using liquid hydrogen. The gaseous hydrogen is then used in fuel cell to produce the power for the microwave generators, which in turn will provide the thrust in the cavity. But also the hydrogen gas can be used in a conventional small jet engine for in-atmosphere manoeuvring, and used as an input to a rocket engine for in-orbit manoeuvring, in space manoeuvring. So we're talking about a typical atmospheric operation of probably only reaching a maximum speed of around 250 miles an hour. We're going to have very low vertical acceleration of the order of 0.05 of a g. That's about half a metre per second. EmDrive will be used to provide the lift, but also the pitch and roll and yaw control, and we will use a jet for propulsion. Now, this is in the atmosphere. Once you move out of the atmosphere, you then start to accelerate to higher speeds, but again you keep the acceleration levels low. Maximum acceleration we would apply to the vehicle would be something of the order of a 0.32 of a g. EmDrive again is providing pitch, roll and yaw control as well as lift, but now the auxiliary propulsion is provided by a rocket. So once you've reached your orbital altitude, you effectively release the orbital module, and that has again a separate rocket engine which gives you your orbital velocity. And the orbital module itself is not reusable, but the carrier vehicle, which is where all the complex stuff is, obviously is. And essentially you would simply come back to Earth in a reverse sequence to your ascent, and achieve a vertical landing. So your ground infrastructure need be no more than an area not much bigger than a typical car park. Okay, look at the performance comparisons. What I've done here is compared EmDrive spaceplane plus its orbital module with a standard Atlas V, which is the current large launch vehicle. I've compared it also with a projected UK Skylon spaceplane with its upper service module, SUS. Not quite sure what that stands for now, but anyway, it's an upper module. It gets you again from LEO to GEO. So if you take a quick look at the figures here on the table, launch mass for EmDrive is roughly the same as Skylon, around 300 tons. Compare that with a total lift-off mass of an Atlas V of about 540 tons. EmDrive gets you almost 50 tons into GEO, whereas Atlas and Skylon, you're talking about the order of 3 to 4 tons. What is extremely interesting and gives people cause for thought is if you actually use EmDrive to launch into LEO as opposed to GEO, you can't achieve such a high payload mass. In fact, it's brought right down to something like 16 tons and now becomes comparable with the Skylon and Atlas. And the simple reason for this is that the whole flight concept for EmDrive is completely different to the classic launch dynamics of either a rocket or a space plane. Essentially what you're doing is obtaining the altitude in a very low energy vehicle, and a large amount of the energy is required to gain orbital velocity. Well, low Earth orbit has a much higher orbital velocity than geostationary orbit, so you are not going to be able to launch such a large payload mass. To a lot of people this is counterintuitive, and you literally have to go through the sums before it all becomes clear. Major factor in the cost driver is the fact that the EmDrive space plane is a very simple construction. The airframe can be no more complicated than a current aircraft airframe. It, as I say, has very little mechanical and thermal stresses on it. And this helps to bring down the cost per launch by increasing the number of launches, and we've put a typical launch number of 500. The reality is, of course, that this would probably be much bigger than this. Again, the idea is to achieve not only airline operating procedures on the ground, but typical commercial aircraft lifetimes. So, but nevertheless, we've put it at 500 as a conservative figure. The end product of all this is that it reduces the cost per launch from something like $110 million for Atlas V, which is the current asking price for a launch, down to something like $11.2 million for a typical EmDrive launch. Now, not only that, of course, is you're launching considerably more payload mass, so that if you look at the cost per payload to geostationary orbit, or geosynchronous orbit as it's sometimes called, you're reducing the almost $30,000 per kilogram of a typical Atlas launch to our calculation of $224 per kilogram. And that, of course, is a huge cost saving and completely changes the whole dynamics of the launch industry. So if we look at the sort of things that we can do with this launcher, the big application that comes to mind is space solar power satellites. There's been a lot of work on solar power satellites. It goes back something like 40 years. And the current state of the various studies is probably well summarised in a 2011 report from the IAA, which essentially said that there are no fundamental technical barriers that would prevent the realisation of large-scale SPS platforms during the coming decades. The most critical challenge, however, is the essential requirement for very low-cost Earth-to-orbit transport. Just to give you a sort of example of what this means, to get 2 gigawatts of power from a solar power satellite, which is, if you like, similar to the output of a nuclear power station, you need to get 6,700 tonnes into geostationary orbit. If you use EmDrive space planes, we could do this probably over about a year by using 3 space planes, launching about once a week, and using robotic assembly, all of which is sort of quite a reasonable approach to building something 6,700 tonnes in orbit. The total transportation costs, we believe, will be of the order of $1.5 billion to get this 6,700 tonnes into orbit. Now, so this is it's less than a tenth of what the IAA study requirement said would be necessary to make SPS viable. They were suggesting they need to spend, they need to bring the cost down to about $20 billion. But compared to the existing costs, it's a remarkable drop. If you are currently flying 6,700 tonnes to geostationary orbit, you would need 1,700 Atlas rockets, and the total transportation cost would be the order of $194 billion. So the reality is that solar power satellites are not going to happen until we can reduce the costs very, very dramatically. And what I'm suggesting is that EmDrive is the only viable proposed technology that can bring the cost down to make it SPS viable. Now, if you're actually proposing putting large masses into orbit to generate power for the Earth, you might also consider what else you could use these for. And the classic, or a classic approach to the raising global temperatures has been why can't we put a sunshade in space? And indeed you can, and again the physics is well understood and has been studied for many years, but again it's the large cost of putting huge masses into orbit that tends to reduce the probability of these ever being taken seriously. But just looking at the total energy requirement or power requirement of the Earth, in 2008 it was something of the order of 16 terawatts. Recent studies have shown that if you wanted to reduce the temperature of the Earth back down to its temperatures before global warming started, you'd need to reduce global solar radiation by a factor of about 1.7%, and this would require the launching of something like 2 by 10 to the 7th tons of reflectors or sunshades into orbit. Now, when you compare that with the masses of solar power satellites, you realise that you would actually get to that mass once you'd launched 3,000 solar power satellites. And that would still only give you about 40% of the power requirement that you're going to need on Earth. So the reality of all this is that if you use solar power satellites to provide all the power that the Earth requires, the actual mass that you would put into orbit will be of the order of 3 times what is necessary to cool the planet. So clearly there is synergy available in these two engineering proposals. And we would need to think in terms of deploying solar power satellites perhaps to the Sun-Earth L1 point rather than geostationary. We would probably use laser power transmission back to GEO to get the power to geostationary orbit, and then microwave from GEO to Earth. But it would put the solar power satellites with their associated very large reflectors in just the right place to provide shading for the Earth. So what you have then is the possibility of solving both the Earth's energy requirements and the need to reduce the Earth's temperatures, all in one solution, and one that is not the sort of science fiction that it would be if you were trying to do it using existing launch technologies. Okay, what else can we use second generation EmDrive for? Whilst we were studying the launcher, we also looked at, hey, could we use this as a long-haul transport vehicle? The end result is a very similar looking vehicle. Will take you from London to Sydney in 2 hours 40 minutes. It'll get you city centre to city centre because it's vertical takeoff and landing, and it's also very quiet. It actually doesn't make any noise. It uses green energy. It's liquid hydrogen fuel. It would get typically 100 first-class passengers backwards and forwards in great comfort, with a cost per passenger mile that is actually below the existing costs of a typical airline. The flight profile is interesting and illustrates the completely different approach to flying that EmDrive will give you. You have vertical takeoff, a very slow ascent, going up using an auxiliary jet as propulsion, and EmDrive for lift. It takes the order of 20 minutes to get you up to your cruising altitude of, in this case, 100 kilometres. Now here you are not completely free of atmospheric effects, but to all intents and purposes you are in the vacuum of space, so you can start to accelerate without all the thermal problems that you normally get. You actually accelerate up to a few thousand miles an hour. Such that your cruise phase lasts of the order of half an hour. Again, you restrict the acceleration to something that keeps your first-class passengers comfortable, well below 1G, so you wouldn't really notice it. At the end of the cruise phase, when you're sort of over the coast of Australia or wherever it is you're going, you start to descend. Again, you're using now EmDrive in the reverse mode to control your descent. Again, it's a gradual descent, and you finally turn on, when you're down into the atmosphere, you finally turn on your jet to give you the manoeuvrability to approach your car park landing space in the middle of the city. Now, all this is completely viable. It's different, it's disruptive, but it's completely viable, and it is cheap, because suddenly you have a long-haul aircraft that is not difficult to build. We were looking at the details of this, and one of my colleagues jokingly suggested that you could build this aircraft out of pressed steel. And it would still fly quite happily, and that's true. So in some ways you could be in the situation where you are de-skilling the building of an aircraft. You're moving from the existing high-tech, highly skilled method of building aircraft to basically automobile manufacture. So clearly there is disruption for the aircraft industry here. Other markets, well, a new scientist once gave a cover illustration of a personal air vehicle, which I always felt was rather nice. But it does illustrate that clearly the famous flying car suddenly becomes possible. So you can envisage automatic passenger carrying vehicles, you've got clean, quiet, vertical takeoff and landing operation, and effectively you have door-to-door transportation. above all, you eliminate traffic jams. As soon as you start going into transport systems that are in 3 dimensions instead of 2 dimensions, you clearly have the potential for uninterrupted journeys. The actual control of these journeys is pretty straightforward. The amount of data you need to flow around a control system for automated flight of this sort is relatively low compared to modern data communication systems, it's completely feasible that we could have a totally new personal transportation system that solves virtually all the problems of our existing traffic. Space applications clearly keep coming to mind. There's space tourism, there's exploring the solar system, there's asteroid mining, and one of the latest studies we've done is actually for the first interstellar probe, where we believe we can actually reach 2/3 of the speed of light in about 10 years using a nuclear power source and an EmDrive propulsion system. Other transport applications, marine is one that has been suggested. Oil tankers and container ships can be propelled at about 1/3 of the existing fuel consumption. You can also use EmDrive for stabilisation and in-harbour manoeuvring. A very interesting transport application was proposed whereby apparently one of the major problems of running railways in cold climates is the traction problems that you get. So suddenly when you don't need to grip the rail, if you use EmDrive as a lift engine, you eliminate all those problems. And of course, if you have to haul large structures or heavy goods across difficult terrain, clearly an EmDrive type hovercraft vehicle would be ideal. So, summary. EmDrive is going to give you a quantum shift in energy and transport. It's going to be an enabling technology for solar power satellites, which have been acknowledged by people who have looked at it very carefully as the only real solution to the Earth's energy problems long term. It gets rid of carbon-based fuel for future transport, replaces it with hydrogen. It's a very disruptive technology. A lot of vested interests are going to suffer, but it will lead to a truly sustainable modern world. And if you want that sustainable world to remain at a reasonable temperature, it would also enable the sort of ambitious geoengineering solutions to be implemented. This next slide, but what it does, it presents a possible roadmap to the development of EmDrive. It starts off back in 2003 with the history, takes us through to 2013, states where we are now, and gives some potential milestones en route to 2023 for the next 10 years, when we should end up with personal air vehicles of around 1 ton, 1.2 ton mass. We'll have spaceplane launches 320 tons, 50 tons to geo payload. We'll have VTOL transport, long-haul transport. 100 people taken around halfway around the world in less than 3 hours, and we'll have deep space propulsion modules. Now, all this is quite feasible, and the roadmap to get there has been planned. So how are we off in terms of actually starting along this roadmap. Now let's look at the different countries in the world. First of all, take Europe. It's fair to say that until very recently there's been no major interest in EmDrive within Europe. Industry, particularly in Europe, tends to be very conservative and is heavily committed to small improvements of what is still essentially 20th century technology. Ourselves, we're continuing theoretical research at SPR. We've recently completed a design study for an all-electric single-stage to orbit launcher. This is to basically, as an improvement to the hybrid spaceplane we were talking about earlier. In America, things are interesting. There are clearly many defence applications which are taken seriously, but to date there's nothing in the public domain. There is a superconducting research program going underway in one private company, though the results to date aren't exactly very impressive. But they're making progress. China is actually the country that seems to be leading the world. The basic research, as I understand it, is now completed. Papers have been published. Even the UK Institute of Physics has published one of their papers. So that certainly makes it respectable. They have a superconducting research program underway, and I believe there is significant commercial space interest within China as well as just the academics. So we have a situation that Europe needs to wake up. Otherwise we will literally be left as a museum of 20th century technology. And more importantly, we will be unable to contribute to solving the major global problems. And we'll be just shrugging our shoulders and leaving it to either America or China, or probably both. EmDrive is a new class of electrical machine. It's one which directly converts electrical energy into thrust, but does not need reaction mass. So it's like a rocket engine, but without the exhaust plume. At its heart, there is a microwave cavity, a resonant microwave cavity, and the special shape of this cavity enables the momentum in the electromagnetic wave, which is propagating inside the cavity, to be transferred to the cavity itself, and therefore you are changing electrical energy into kinetic energy. Well, it all started way back in the depths of the Cold War, actually. There was considerable concern over the accuracy of the guidance systems of the strategic missiles that were being deployed at that time. And it was of such concern that a small group of R&D engineers was put together. I was part of this group. And we were actually told to think the unthinkable, to try and come up with solutions to this problem. And it was during that absolutely brilliant exercise that I actually got my early ideas for EmDrive. The solution wasn't EmDrive, and I went off and did some quite interesting things for the British Army after that. But in 1980, I was in the middle of the desert when the Iran-Iraq war broke out, and it was all very alarming. And so when I got back to the UK, I decided I'd better find a new career path. And I joined the space industry. And it was while I was working on the design of the Skynet 4 communication satellite that it dawned on me that what I'd been working on previously, some years before, would be ideal for propelling satellites, particularly military satellites in this case. So that was really where it all came from. Oh, the eternal question. No, EmDrive does not break Newton's laws. In fact, it works because of Newton's third law. EmDrive produces thrust in one direction, and if it's allowed to, it will accelerate in the opposite direction. Momentum is conserved by this process, and that's what Newton's third law is looking for. In fact, EmDrive is based purely on classic physics, the physics of Maxwell, Newton, and Einstein. There is really no need to bring in exotic physics to explain EmDrive. We don't need quantum vacuum plasma effects, and it is most certainly not a warp drive. No, it is not reactionless. It is propellantless, or propellant-free perhaps, but in real life there's no such thing as a reactionless drive. Newton doesn't allow for it, and I don't attempt to build one. Well, the main players are still in the UK, China, and the US. However, there are 3 other countries that have serious programs running that I know of, and there are also a growing number of university departments and private individuals who are trying to replicate our first experiments. This is of concern because an EmDrive is a potentially lethal device, particularly if you are close to measuring reasonable amounts of thrust. It means you have a very high Q cavity. You are putting in a significant amount of input power, and this makes it quite dangerous. So the way to handle the device is the way that I learned in my early career as a defence contractor. You must devise rigorous, strict, and knowledgeable safety procedures before you start experimenting with EmDrive. It has the potential to kill you, and you must obviously bear this in mind. It's great fun, and it's very tempting just to rush in and test it, but you must consider the safety aspects before you do this. Second generation EmDrive, which is the superconducting version of EmDrive, will give us eventually low-cost access to space. Now this will make solar power satellites economical. They will in fact be far cheaper and considerably more safer than nuclear power stations, for instance. What at present is really not economically viable will become the obvious source of clean, green electrical energy. Now, the space planes that will be developed and used as launch vehicles for this low-cost access to space can also be used, can be developed into long-haul aircraft. They will give vertical takeoff and landing, so you don't need runways anymore. You'll get city center flights. They'll be quiet, green, and importantly, the airframes for these aircraft or space planes will be essentially low-stressed airframes. What we're proposing is that we use liquid hydrogen to actually cool the superconducting cavities, and then the hydrogen gas which boils off from this cooling process is used in fuel cells to provide the electrical energy into the EmDrive engine itself. So while you're going through the atmosphere, you're simply using liquid hydrogen fuel as fuel. Once you get out of the atmosphere, you'll need a small amount of liquid oxygen as well. But the end product of the process is simply water. So, okay, you'll get a few more vapor trails, but it's clean and green. Well, what we're proposing in our development program is that we start off with small-scale UAVs, unmanned aerial vehicles, and these will be used to as part of the development process. But clearly, once we have these flying, the next step would be simply to scale them up to small personal air vehicles. So possibly one of the first wide-scale applications that we may see are the longed-for flying cars. So perhaps there is a solution to the city traffic jams. Well, I think there's been an interesting study done in Europe as to how you would actually incorporate a flying personal air vehicle into society, and the thinking is that it will almost certainly be an autopilot. You won't fly these yourself, and you won't own them. I'm sure you'll simply ring up for a vehicle to take you from A to B. It will arrive, land outside your home or office, and will automatically take you to wherever you want to go. This seems to be a rather more sensible way of incorporating these vehicles safely into the infrastructure, the traffic infrastructure. So I suspect, in the long term, the cars and other vehicles that we have today will become purely for leisure use and perhaps of historical interest only. Yes, we did. We have done a number of design studies, and one that I've reported on in previous conferences is the fairly large 300-ton spaceplane for delivering 50-ton payloads into geostationary orbit. Now, these spaceplanes operating on a regular basis will bring the costs per kilogram of payload to geostationary orbit down by a factor of 130 compared to the existing launch vehicles. Now, this is a huge cost saving. It's better than 10 times the cost saving that has been thought necessary to make solar power satellites viable, for instance. So you will have then the ability to put large payloads, 50 tons a time, into orbit. And therefore, if you can put solar power satellites into orbit, you can also put solar sunshades into orbit. The other important thing to note is that these sunshades will be totally controllable, because first generation EmDrive, which will be used for in-orbit applications, will give you total control over the angle of these sun shields, and therefore you will be able to control them on basically a minute-by-minute basis to give you the exact amount of thermal control that you need. Well, this is a particularly interesting aspect of the type of vehicles that we're proposing will use EmDrive technology. Essentially, they are vehicles. They're called space planes. They operate both in the atmosphere and above the atmosphere in space. And the thing about them is that their flight envelope is such that they don't go fast inside the atmosphere, and they don't accelerate very fast. So the stresses, the thermal and mechanical stresses that we see in current aircraft will be very much reduced. And because in effect you only go fast when you're in vacuum, it makes it clearly a lot more efficient way of flying, but it also, as I say, means that the airframe can be built using a much more low technology. In fact, it's very suitable for the sort of technology that is currently used in the car industry. And therefore, we can envisage high volume production of these launch vehicles using low-cost technology. Some of it is already being developed by the automobile industry. I mean, the obvious example is hydrogen fuel cells. I mean, that's well into development now for cars, and will apply directly to space planes. So I don't believe that it's a cost factor that is going to hold up the development and application of EmDrive. Clearly, the existing infrastructure and the large industrial vested interests that, that produce this infrastructure are going to wish to slow down or even suppress such new technology. Now, this is not a new problem. Any disruptive technology has this problem. However, the world's problems are getting so serious that the politicians and the industrialists should start to take note of this. And I'm sure if they don't in the West, then we will find the developing countries that don't have this inbuilt set of vested interests will simply take over the technology, develop it using, as I say, fairly low-cost manufacturing techniques, and will simply solve the problem for us. So there's a challenge there. It's rather more a political challenge than a technical challenge, I would say. Okay, well, in 50 years' time, I believe that EmDrive will help us to dramatically reduce our dependence on fossil fuels. This in itself will help with climate control, or reducing the rise of temperature of our world. I also believe that the sun shields will come into play to finally counteract the climate change, temperature change. So I think we will have cracked those particular problems. I think we will have a much more user-friendly transport arrangement. Everybody wants to get rid of traffic jams, and it is a nonsense that we spend so much of our time wasted in these sort of situations. So I think EmDrive is going to offer us a much more benign world. I also hope that it will enable us to meet the original intention of EmDrive, which is to make access to space much more low cost, to enable us to move more freely in space once we're there, And certainly it should give us short flight times to all the planets of our solar system. And I would expect, certainly within 20 to 30 years, to have launched our first probes, unmanned probes, to the nearest stars.